Hello everyone, this is Ramin Madani presenting our MATLAB GUI application, which is dedicated for the analysis and processing of hyperspectral images. Our group consists of Dr. Mart, Dr. Aleksei Tepljakov, and myself. We're all from Tallinn University of Technology, or Taltech. To get more familiar with the hyperspectral images, it may be useful to imagine RGB images. In an RGB image, there are 3 different bands, and each of these bands is assigned a wavelength. So we have only 3 bands, and each of them have a wavelength. But in hyperspectral images, we have way more bands, nearly hundreds of bands. So for each image, you can guess that there are significantly much more information available in a hyperspectral image. And for each of the band of a hyperspectral image, there is a wavelength assigned. And also we can say that wavelengths that are possible in hyperspectral images go beyond the range of visible. So for the camera that we had, which is a specific IQ camera, it was 400 to 1000 nanometers, and it had 204 bands. Consequently, for each RGB image, in each pixel, we have only 3 values. And as you see on the left, these 3 values could be graphed on an intensity wavelength diagram. But for a hyperspectral image, we have way more values for each pixel. As you see on the right, in the wavelength intensity values, we have a continuity of points which adds up to hundreds of points, and so we can make a graph out of these points. This graph is called a fingerprint and is specific for each pixel. When the hyperspectral cameras were introduced in 2010s, a few consequences followed. For instance, a wider population could access the HSI technology. People in interdisciplinary fields like mechatronics could benefit from HSI, and also different applications were added to the previous applications. So a new software with new features were needed. That was the reason that we thought of this application. We decided to write a software that is tailored for the users of portable hyperspectral cameras specifically. Also, it should be usable by people in science and engineering community with an easy-to-use interface. So simplicity is the first thing that we had in mind. Also, it could be used for educational purposes. There are many softwares on the landscape of the market these days, but each of these softwares have deficiencies. So we try to solve these deficiencies. For instance, some software are too simple, some of them are too complex to use, some of them have no GUI or GUI, and some of them are not free. So we try to solve these. The interface of the application that we worked on consists of different modules. As you see in the display tab, we could extract the fingerprint of a point or a set of points. We could get the intensity map, which is a map of the intensity values of the pixels. And also we could get the image which corresponds to a specific band of a hyperspectral image. In this tab, we could also save the fingerprint and add a point or a fingerprint of a point as a new material, so it could be used for classification purposes later on. On the histogram tab, we could get the different histograms of the image. As you know, the equalized histogram has many applications in image processing and machine vision. We can also get the results on the left as 2 images, and we can select each of the bands of the image to be used for the process of getting a histogram. For the false RGB, As we said, there are many possibilities for bands in hyperspectral images, and each of these bands could be interpreted as a red, green, or blue band of a color image. So by selection of different combinations of these three values for different bands, we could get different images. In our case, 8 million different color images were possible just from one hyperspectral image. So as you see, by selecting the values, different images could be produced, and also a point cloud of the image in the RGB space could be produced. There are different histograms, as you see in the backward image. And so this is mostly what concludes our software. As an example in the real world, we studied a case. The application is when we have two very visually similar objects and we want to make a distinction between them. In robotics and mechatronics applications, such as pick-and-place algorithm, it has great use. Also, when we want to make a recognition, this is also useful in that way. Let's try and see if we can make a distinction between the two apples below. Here we have two apples that are very visually similar. We get the fingerprint of each of these apples. And as you see, the fingerprints are very similar, but in 3 points, as you see with the arrows, around 711, 750, and 990, they are different. So we could be hopeful that if we select these three bands and assign them RGB colors and then get the merged image, we could find an image which can show the difference between these two apples clearly. And that is what happens in the image below. You see, with the correct selection of the bands, we could make great, clear and great distinction between these two apples. And this is one of the applications of our software. As you see, the flow that is needed to be followed by the user is the green path, but there are many other things that could be done to solve this problem also, or as further applications. You could see with black. As a conclusion, we could say that with simplicity and interpretability, by increasing the usability or making usability, and by making available this application for free and increasing the accessibility, we could reach our initial goals. And so we could say that the initial objectives are fulfilled. And now we're ready for your questions.